Hi there, and welcome to Telefunkian. Today, we have another installment in our series on the Powertran Transcendent 2000. We're going to be opening up this instrument and giving it the spa treatment, refurbishing it so it can give us another 4 decades of enjoyable service. As described in our introductory video, the Transcendent 2000, or T2000 for short, is a single oscillator kit-based mono-synth released in 1978. As cool as this synthesizer is, nothing lasts forever. So in this video, we'll be addressing the question, what, if anything, should we do to this specimen to keep it running like it should? In this video, we're working with a synthesizer that's been imported from the UK to Canada. The first order of business will be to convert the power supply to the voltage used here in North America. We'll then recap the power supply, bring it up slowly on a variac, and make sure it's working as it should. We'll take a look at the so-called Tempco resistors supplied with the T2000 kit. Back in 1978, properly calibrated temperature-compensating resistors were not as readily available as they are today, so the company Powertran used something that might best be described as a kludge. We'll take a look at the performance of Powertran's solution and compare it to some modern Tempco equivalents. We'll examine and find that we need to replace the tropical fish capacitors in the instrument, and we will of course clean all the switches, potentiometers, and keyboard contacts. One final thing we'll cover is replacing the knob brights that have a tendency to fall out and get lost from instruments of this vintage. Other videos on our channel will cover the diagnosis and repair of this instrument, a subject that's beyond the scope of the current video, as well as the tuning and calibration of the instrument, and a modification owners of the T2000 may wish to consider to address what's been characterized by some as a signal-to-noise issue with the synthesizer, but I believe it's more properly described as a gain staging issue. If any of these sound interesting, please be sure to check out the other videos on the channel. If you're looking for more information on the Transcendent 2000, there are a handful of good YouTube videos on channels such as Synthmania, Look Mum No Computer, Mark Jenkins' channel, and Mindburner, whose channel features classic 80s synths and includes a video he's made describing the T2000 and another where he uses it in a performance. Special thanks to Mindburner for allowing me to sample some of his video in our opening montage. I hope you enjoy this video. Let's get started. So here we have the transformer for the T2000, and it's a transformer made by a company called Canatron Transformers. And this is an English company that unfortunately went out of business in the 80s and doesn't exist. Their website is no longer. But the good news is that they have a label on the transformer which indicates the voltages and the like. And so what we're looking at is a transformer that has a dual winding suitable for 50 or 60 hertz, 240 or 120 volt input. And it outputs two 15 volt sources, presumably with a center tap ground serving as 0 volt potential. And this allows us to generate a positive and negative 12 volt power supply from the output of this transformer. In order to use this in North America, we're going to have to do a little bit of rewiring, and that is that this junction here, which joins the two windings here in series, will have to be changed so that we can arrange for these windings to be in parallel. So we'll need to connect the 0 and the 0 and the 120 and the 120, and that is how we'll be wiring the transformer. But just so that we don't make any terrible mistakes, we're going to be checking the wiring with the voltometer once we disconnect the transformer, or at least a couple of the wires from it. I'm doing this around the camera and a number of other things, so hopefully I don't obscure what's going on here. Okay, so if the universe unfolds as it should, what we should find is that this and this, these two terminals, are connected to one another by a resistance, which is similar to the resistance that we'll find in between these two terminals. And so I'm going to set about measuring that. The resistance between these two terminals, 419 ohms, and between these two, 369 ohms, and we shouldn't be confused or surprised about that difference. There's no connectivity here between these two terminals and none between these two terminals, and that's what we should expect. Yeah, and so this is one winding here from here to here. This is another winding here from here to here, and we'll just wire these windings so that they're in parallel rather than in series, and go from there. Oops. Well then, that wasn't attached very well in the first place. So let's see what we can do about that. They certainly use lots of solder. There we go. Okay, so from where I'm sitting, I can't see what I'm doing, so I hope that is okay. Yes, it's okay. It's not the prettiest job in the world. Okay, now what's going to happen when we apply power to this? What are we going to get out of the back end? Okay, so of this apparatus connected to a variac, which allows me to adjust the voltage and feed in whatever voltage I want into the power supply. And so I should be able to turn on my variac, which is currently at 0 volt, and begin to power it up. And as I do so, we should begin to see AC voltage appearing here. And as I increase the voltage, we're now at 37 volts, 38 volts, and we have 5.5 volts AC coming out of the transformer. And we're at 70 volts, about 103 volts, and we have 15.8 volts coming out of the transformer. And there we are at 120 volt. And we're drawing essentially no power, but we have 18.7 volts or so coming out of the transformer. And that's probably about right. That's about what we might expect for non-rectified voltage coming out of a 15 volt transformer. Turn that off, check the other winding, and make sure the other winding is intact. Turn it back on, and at 120 volts, there we are, 17.8 volts, or 118, 119, 120, yeah, around 18.1 volts. And so both windings are giving us 18 volts, and that should be adequate going into our power supply. So with the transformer plugged into the variac and set at 120 volts, I'm now going to check the power supply in the T2000. Green here is ground. I'll just set my probe there and touch the blue wire, and what have I got? I should have minus 12 volts. There we are, minus 12.037 volts. And if I touch the red wire with my red probe, I've got plus 12.03 volts. So it appears as if the power supply in the T2000 is working. And that's great news. Though I'm sure that it could stand with a recapping. It's good to know that the integrated circuits and the like on the power supply are functioning as they should. These capacitors, 1000 microfarads, they're 40 years old. They should probably be changed, and there's some tantalums on there as well. I'll probably swap those out. I'd like to look at the power supply rails and measure the amount of noise on the rails before doing anything. And so I'll hook up an oscilloscope, plug in the instrument, and see what happens. So we're looking at the negative supply rail, and it is centered around negative 12.15 volts DC. And we've connected the oscilloscope to the green, which is the ground, and the blue, which is the negative rail. And you can see there's a bit of noise on the supply. If I stop the digital oscilloscope, you see that it's maybe, I don't know, averaging around plus or minus 10 millivolts on each side. And we'll move this over to the positive rail and see what this looks like. There's the positive rail, which again is a bit high relative to the 12.0 nominally, but it has a comparable amount of noise on it, maybe plus or minus 10 millivolts on average or so. It's looking like that, and there's relatively little, I guess, periodicity. If we were at 1 mic or 10 micro seconds per division, and if we change that, you can see that there's no apparent periodicity associated with that. What we'll do is set out to change the capacitors in the power supply and determine whether or not that makes any difference really to the extent of noise that we're experiencing here. Yeah, so that's what our positive rail is looking like right now. So we'll remove the power supply so that I can get underneath the board and change out these reservoir capacitors and see what happens. This is a look at the power supply board from the T2000 out of the actual instrument. And I can't actually get it much further out than this because I've gone and soldered the ground from the power cable right into the ground that feeds into the power supply. So unless I unsolder that, this is as far as we can go. What you can see on the back side is you can see that there is some labeling and the like on the back side, but I don't really see any polarity labeling, obvious polarity labeling for the capacitors. And so I'm going to have to be careful as I take these out to make sure that I denote the polarity somehow so that I don't get mixed up. So what I'm planning to do is replace not only these 40-year-old electrolytics, but there are 3 tantalum capacitors on this board as well. I'll be replacing those because these are somewhat famous for shorting. And we don't want that. That could potentially blow up either of these 2 chips. And although these chips are chips that we can still acquire, we want to protect their integrity. And I'll also measure the various diodes and the like and make sure that everything's okay. So in the meantime, I might as well bust out my Denon solder sucker and use that. Received a bit of feedback on the channel. People asking why I don't have a solder sucker, and not only do I have a couple solder suckers, but I've got this guy, which I've recently repaired, and will attempt to use it on this job here. So let's see. Okay, let's have a look at these and see what we can see in terms of ESR. Well, okay, 0.085. So that's right on the limit, actually a little above the limit for 1000 microfarad cap at 25 volts. But still, it's not terribly bad given how old these capacitors are. Try this one. And this one is actually within specifications. However, they're both going to be replaced. And what will we replace them with, you might ask? Got a couple of these guys, and they should barely fit. And these are Sprague caps, and we're looking at 2200 microfarads. And ESR that is almost in the same zone. However, these are capacitors that are good to 105 degrees. I'm not sure about these ones that we're taking out, the ITTs. Yeah, so the ESR is in the same sort of zone as almost brand new caps. So that's really quite impressive, I have to say. So we want to bend the leads such that the value of the capacitor is going to be readable. Okay, so I'm going to pull out a few tantalum capacitors. And this should be a 2.2 microfarad capacitor. And it is very good. Oh, no, it's the same. ESR 11 ohms. Well, we'll see about that. Okay. Hopefully this is the correct polarity. Be interesting if it isn't. Ten ohms. Wow. Okay, garbage. Let's check this other guy. Similarly, a rather high ESR. Yeah, so these need to be replaced. We need it, and in the first case, the positive goes from here to here across the ground, and the positive on the output. Yes. This is C7. And the next, we have the positive going to ground and the negative going to the negative output. And that's right here. We don't want to get these mixed up because if we do, tantalum capacitors have a terrific habit of exploding, which could be exciting. And finally, we have positive towards pin 5 and 6 and negative to ground. Which was here and here. I'm very curious to see if these new tantalums improve the noise on the power supply at all. And while we're in here, let's take a look at all these resistors and the like. Where are we? Oh, we've got our voltometer configured incorrectly. These are supposed to be 3.3 ohms, and they're measuring 3.5, but my voltometer is measuring about 1/4 of an ohm. Yeah, so I think we're good here and good here. So this is a look at the positive rail on the power supply. We're looking at 12.18 volts and a ripple, if you will, of about 3 millivolts using a 1 millisecond per division time base on the digital oscilloscope. Now, if we change that to, say, 10 microseconds per division, we'll see that the number changes a bit to about 6.86 millivolts RMS. But nonetheless, it is what it is. I'd say there might be about a 3 millivolt RMS signal on there. And if we move this over to the negative rail and adjust our scope, we see again we have about a 3 millivolt RMS noise on the scope. Let's try that with the meter. If we try to visualize this with the meter, we're going to see Well, we're on auto, so the meter is having a hard time with this. Move off of auto onto AC. AC millivolt. There we are. Yeah, we're looking at about 3 millivolts RMS AC noise on there. 2.5 millivolts. And on the positive rail, again, about 2.5 millivolts of ripple, according to this meter. So we can live with that. Another thing I wanted to mention was the incorporation of safety capacitors, X and Y rated safety capacitors, both across the live and the neutral, and from the live to ground. And this is meant to be an RF noise suppression approach. I've taken the main PCB out of the T2000, and this is for a couple of reasons. One of which is I'd like to replace these electrolytic capacitors, and it's a little easier to get access. There are a number of tantalum capacitors on the board as well that I think that we may replace, and we may replace a number of these single turn trimmer potentiometers. I believe there are 8 trimmers spread around the board. We may replace some of those with multi-turn trimmers that will be a lot easier to use to calibrate the instrument. In addition, we have a number of potentiometers that I've indicated with masking tape on their shafts, which need to be cleaned, and you can see that we can spray contact cleaner into them from this direction, but it's a lot easier to make sure that that's done properly with the board out of the instrument. And then in addition, there's a tremendous amount of flux which remains on the board from its original assembly, and I'd like to clean all of that off. And again, that's something that'll be a little easier with the board out of the instrument. In addition, I may be replacing these resistors here. These are wire wound resistors. And when I originally saw them, I was under the impression that perhaps they were temperature compensating resistors. And they're actually not proper tempcos. They're a bit of a kludge as a result of tempcos being relatively difficult to obtain when this instrument was put together. And so these resistors will be replaced with proper temperature compensating resistors, and that should make for a more stable tuning. I've got those on order, and they should be here any day now, which is why I've pulled the board, and I'll begin work while I'm waiting for those. And hopefully when they arrive, we'll be all ready to go and able to tune this instrument and get it buttoned back up again. Before we examine the tempcos in the T2000, some discussion may be in order. Tempcos are temperature compensating resistors, and as their name implies, they're placed in circuit to compensate for the effects of temperature on other parts of an electronic circuit. In our present case, their job is to help stabilize the voltage-controlled oscillators from the effects of temperature on the parts of the circuit that determine oscillator pitch. The performance characteristics of most electronic components change to some degree with changes in temperature, and resistors are no exception. In most situations, these changes are relatively insignificant, but in certain cases, resistors can be designed such that their resistances change in a controlled, predictable manner in response to changes in temperature. Resistors can have either a negative temperature coefficient, where their resistance decreases in response to increases in temperature, or a positive temperature coefficient, where their resistances increase in response to increases in temperature. Temperature coefficients are usually specified in data tables when ordering components from your favorite supplier. You may be familiar with the use of negative temperature coefficient resistors as thermistors. They're commonly used as current limiting devices in the power supply of audio amplifiers as a means of limiting inrush currents associated with power on and the initial charging of large capacitor banks. They are especially useful addition in tube equipment when tube-based rectifiers are replaced with solid-state replacements. Most, but not all tempcos and synthesizers have a positive temperature coefficient. The reason tempcos are used in analog synthesizers is that many voltage-controlled oscillator circuits utilize transistor-based exponential converters in the conversion of control voltages to currents and subsequently oscillator pitch. Because transistors are very sensitive to changes in temperature, and exponential pairs exhibit non-ideal behavior in response to temperature, temperature-compensating resistors are used to adjust the voltage presented to the base of the exponential pair in an attempt to maintain a constant pitch. If the tempco is missing, improperly coupled, or otherwise faulty, the result may be an unstable oscillator pitch. What's shown here are three different implementations of this basic concept, taken from the schematics of the T2000, the ARP Odyssey, and the Roland TB303, where in each case we see a tempco between the base of the transistor sensing the VCO pitch control voltage and a voltage reference, either ground or, in the case of the TB303, 5.333 volts. The T2000 design calls for a 1000 ohm resistor with a positive temperature coefficient of 3400 parts per million per degree Celsius. As such things were not widely available at the time, what was included in the kit was an 870 ohm copper wire wound resistor that was placed in series with a 130 ohm metal oxide resistor to approximate a 1000 ohm tempco with a 3400 part per million per degree Celsius coefficient. So today, more than 40 years later, we're asking the question, how good is this solution? Does this combination function as a tempco, and if so, what is its temperature coefficient? How does this combination compare with modern tempcos that may have a smaller footprint, less thermal capacity, and might be expected to be easier to thermally couple to the transistor array chip housing the exponential pair? In order to find out, we'll start with a simple experiment. This is the highly scientific setup that we're going to be using to assess these temperature compensating resistors. So right now we have 24.9 degrees. According to this. Or 24.7 and 1010 ohms. 1009 ohms. And we'll gradually increase that. And the way we'll do that is with a little hot air station here. And applying that from a distance, quite a distance, about a foot or so, in an effort to heat up the platform gradually. Dozen 36. After collecting data measuring the resistance of 3 different 1000 ohm temperature compensating resistors between 25 and 50 degrees Celsius and graphing the results, we're able to calculate the temperature coefficient of resistance for each tempco. The first thing we see when we graph the results is that each tempco exhibits a linear increase in resistance with increased temperature, which is what we expect. The slope of the line is a reflection of the TCR, with a steeper slope representing a larger temperature coefficient. Both the originally supplied resistor combination and one of the modern replacements, the Anika ohm tempco, exhibit identical TCR of 2980 parts per million per degree Celsius, while the modern KRL tempco exhibits a TCR of 3656 part per million per degree Celsius. The original tempco is furthest from its nominal target, while the KRL is closest, but is still 4.4% off target from the nominal value of 3500 part per million per degree Celsius. So what should we do with this information? Well, the good news is that the original combination was indeed performing as a tempco, and that we have modern replacements to consider with reduced thermal inertia. So what I've done in this synthesizer is used an Anika ohm 1000 ohm tempco with a nominal TCR of 3300 as a replacement for the original combination in the VCO. This resistor has approximately 1/8 the mass of the original wire-wound resistor and should be much more responsive to small temperature changes in the circuit. I used a KRL in the VCF, which also uses a tempco, but is less sensitive to changes in temperature, which will at most affect the timbre of the filter rather than the pitch. What we've done so far is actually a fair amount of work. We've replaced all the electrolytic capacitors. We've replaced the tantalum capacitors. We've replaced all of the film capacitors except the polystyrene capacitors. And we've also fitted new multi-turn trim potentiometers. We've cleaned all of the control potentiometers. We've cleaned all of the switches. And we've actually replaced the tempco resistors as well. You'll recall that we had a rather bulky tempco, and so we've replaced that with some smaller tempcos that may be more heat responsive. Well, these are the so-called dead men, all of the parts that I've replaced in the T2000. And we have here a number of electrolytic capacitors. I think I've discussed these already. There's really not too many of them. I think there's about 5 or 6 at the most. And we have a number of tantalum capacitors, which have been refreshed with new tantalums. We have these single-turn potentiometers, which I've replaced with brand new multi-turn potentiometers. And we have these wire-wound resistors that we've discussed that were functioning as temperature compensating resistors that we've replaced with resistors which have much smaller footprint, and accordingly we believe they'll be much more temperature responsive. This is an example of one of these. This is one that after quite a lot of elaborate lead bending, I was able to have it sit down on the transistor array chip that it was sensing the temperature of, but however, after I'd done all this lead bending, I found that I'd created an open resistor and replaced it with another temperature compensating resistor. And then we have these. These are what we refer to as tropical fish capacitors, and they get their name. You might not be surprised by the rather bright colors that you can see here. This is actually a color code, and it denotes the value of the capacitor. And it's a color code that is very similar to that which is on resistors. And in this case, we start reading it from the top of the capacitor, the first color brown indicating a 1, black 0, and so on. And the last color on the body of the capacitor denotes the tolerance of the capacitance. These are a film capacitor, and I've replaced all of them. And the reason I replaced them was because they're all exhibiting early signs of a motive failure that I'm not sure if you can see here. But these are epoxy dipped, and in every case, the epoxy on the capacitor has cracked and is beginning to peel off the capacitor. And what this does is it allows for ingress of water, moisture that's in the atmosphere, and that alters the capacitor value. And so this is a well-known failure mode for these old capacitors, and as beautiful as they are, I've set about replacing them with new replacement film capacitors that should last for years to come. So a relevant question may be, well, how did they test? And I did test a few of them, not all of them. And those that I did test, tested okay so far. But given the known failure mode and the fact that they're well on their way towards failing, I replaced them with new ones. These are examples of some of the new film caps I use. These are Nichicons, 150 nanofarad, 50 volt capacitors. Another style that I used were these orange drop knockoffs. These were from our local electronics supplier. You can see here 5 for $1. They're not terribly expensive. And my preferred capacitor type would have been these WEMA type, but given the shipping and sourcing issues that we're having, I elected to just use these orange drop type that I was able to get locally. So that's about it in terms of parts that were replaced, in addition to this transistor array, which was part of a failure and was replaced in a repair that I'll describe in a subsequent video. It won't be covered in today's video. I wouldn't consider it to be regular maintenance, but really this is representing not too terribly much money, maybe a few hours of work, of course, but all in all, we're looking at certainly less than $50 worth of parts used in the refurbishment of this instrument. So a worthwhile investment, I would suggest, and I hope you've enjoyed watching the video. Well, one more thing that we need to address whenever we're refurbishing a synthesizer is we need to make sure we get all the knobs clean. And there are, of course, I guess 22 odd knobs on the T2000. And what I've done is I've just soaked them in water with a little detergent and then brushed them with a brush, and that's got most of the dirt off, although not all. But one of the things you may notice here is that a couple of the knobs are missing their brights. That's what these little metal inserts are referred to as brights. And these brights just sit in here and get glued down with a little bit of contact cement or some other kind of semi-flexible adhesive, and sit there quite nicely and as the name might imply, brighten up the knobs a little bit. Well, as it happens, a number of these have fallen out over the years, and the previous owner has lost them, and so we need to replace them. They're not the easiest thing to find, but I did manage to find a vendor who sells knob brights, as these are called, on eBay, and these are brushed aluminum, and this is what they look like. They're very, very similar. These have a plastic coating on them, which I will remove from this one so that we can see just how similar this is to the bright that is on the knob. And there's very little discernible difference. They're a pretty good match. Let's just leave it at that. However, where they don't necessarily match terribly well is in terms of the size. So the knob brights on the T2000 are a little less, well, a little less than, I guess, the 9/16 of an inch that is represented in this bright. This is a 9/16 inch bright, and it needs to be just a tiny bit smaller. So we have a nice low-tech solution for that, and that is a piece of sandpaper. And this is 600 grit waterproof paper. And just with a little bit of sanding, we can refine these such that they will then fit in the insert, which is carved out of here. So if you're looking for knob brights for this synthesizer or any other, this is the vendor from whom I obtained these. Nationwide Radio and Equipment Sales. A gentleman named Mark Olson, who goes under the name KE9PQ on eBay and has a website, ke9pq.com, where he sells knob brights of various sizes. And so if you're ever looking for them, you can obtain them at a reasonable price. I think for 6 of these, it was about $8 or $9, and then maybe another $10 shipping. I actually got 24 of them for some reason, even though I don't quite need that many. But regardless, so I'll set about filing these down ever so slightly to make them fit into the knobs, glue them in place, and then I'll have a set of matching knobs with the original configuration that was supplied with the synthesizer. So I thought I'd just share that with you. Well, that brings to an end the technical portion of the video. The recording that follows is after the final calibration, tuning, and gain stage modifications we touched on earlier, all of which will be featured in our other videos. Thanks for watching. So I have the Transcendent 2000 connected in the studio, and we'll be recording directly into the computer and hopefully demonstrating some of the sonic capabilities of the instrument. Enjoy. So the first thing we're going to do is walk through some of the waveforms. And we're currently on the triangular waveform. Using the shape control, we can change that to a ramp, or more commonly known as a sawtooth here in North America. We have, of course, a pulse, square wave. And by changing the shape, we can modulate the duty cycle. So pulse wave modulation. And this can be modulated with the LFO. Similarly, the triangular to sawtooth can be modulated with the LFO as well. And we have the ability to modulate the pitch with the noise generator. Also, the ADSR envelope will modulate the pitch. And the LFO, either in the triangular configuration, as is this case, or in the square wave. And rather uniquely, I believe, we have the ability to mix these two and modulate the pitch with both the triangular waveform and the square waveform at the same time. And you can hear that clicking over. At the end of the square wave. We have, of course, a noise generator, and the noise can get quite loud relative to the other waveforms, which I find to be quite useful. Especially, it's particularly useful in the context of percussive effects. Right now, we're listening to the VCF all the way open, and it's on low-pass filter. You can see it goes very, very low. And quite piercingly high, above 20K. It functions as a bandpass filter as well. And you can see just how low it goes. And of course, we have a very powerful resonant filter in this instrument, which will self-oscillate quite easily. And this is after taming it somewhat with a modification that we'll describe later in a subsequent video. At the low end, we're currently roughly around 20 hertz. And of course, we can go much lower than that. We have the ability to modulate the filter with an attack and decay envelope. And this can be applied either in the positive direction, which is achieved by turning this knob counterclockwise, or it can be imposed in the negative direction, as will be demonstrated in a moment by turning it clockwise. Here we go. And we're still in bandpass filter mode, keep in mind. We have repeat functions as well. And the speed of repeat is modulated by or controlled by the LFO. This may get a bit loud in a moment. For those of you who like your techno style kicks, although this is again still in bandpass mode, we'll come back to this in a moment in low pass mode. this is back with the low pass mode of the filter. A bit more richness in the harmonics. Again, for you techno kick aficionados, so there we have it. A little taste of the Transcendent 2000 and its sonic capabilities. Not highlighting my playing skills as they're somewhat non-existent, but nonetheless, you'll agree this is a pretty interesting and fun instrument. I'd also like to point out, with respect to the so-called noise floor on this instrument, we're looking at about minus 126 dB compared to the minus 6 or maybe even minus 3 dB at peak that we're able to achieve with the instrument. So I think we have about 110 decibels worth of noise floor or headroom, which is more than adequate. So this is a very quiet instrument when it's properly set up and calibrated. Thanks for watching.